In this video, we are going to study how many types of polarization in dielectrics. Okay, so when the specimen is placed inside the dielectric field, that means polarization due to four types of process. So, what are those four? Electronic polarization, ionic polarization, orientational polarization, and space charge polarization. So, let us see one by one. Okay, now the electronic polarization. The polarization means we are separating the dipoles by applying a field. So, what is electronic polarization? Let us see. So, the displacement of the positively charged nucleus and negatively charged electrons of an atom in opposite direction on application of an electric field, that results the electronic polarization. That means whenever we are applying a field to the specimen, what will happen? The positively charged nucleus and negatively charged electrons are moved away from those two. That means they are displaced. So that phenomena is said to be a electronic polarization. See, whenever the field is zero, the nucleus is at the center and the electrons around the revolve around the nucleus. So whenever we are applying a field, induced dipole moment in a field, that means center of gravity that will displaced. Okay, so those two are displaced. So when electric field is applied to electron, cloud shifts towards the positive end of the fields. So the electron cloud shifts towards the positive end of the field. So as a nucleus and the center of the electron could be separated by a certain distance, then the dipole moment is created within each atom. So whenever the separation starts, the dipole moment concept arises. See, now the extent of this shift is proportional to the field strength. Okay, dipole moment we are representing as mu. So electronic dipole moment is mu e, that is proportional to field E. Now mu e equals to alpha E into E, that is alpha E is known as electronic polarizability and it is depends on the temperature. Okay, now let us see how we will calculate the electronic polarizability. Okay, whenever there is no field. Next, in presence of field, the dipole moment concept arises. So the atom consists of a point nucleus of charge plus Ze surrounded symmetrically by an electron cloud of charge minus Ze and a sphere of radius r. Okay, so in the absence of electric field, the centers of negative and positive charge distribution coincide, hence dipole moment is zero. So there is no dipole moment. When the electric field applied, whenever we are applying some field, due to Lorentz force, the electrons move in the opposite direction of the field, that is, two charges separated by a small distance. So, when the nucleus and electron cloud are displaced from their equilibrium positions, an attractive Coulomb force come into play and it will tend to maintain the original position. So, whenever we are applying the field, what will happen? The nucleus and electron cloud are displaced from their equilibrium positions and an attractive Coulomb force come into play and it will tend to maintain the original positions. So when these two forces are equal and opposite, then there will be a new equilibrium between the positive and negative charge of atom and hence its dipole moment is increased from 0. So initially the field is 0, automatically the dipole moment is also 0. So whenever the concept arises, that means there is a equilibrium condition, a Coulomb force is maintained, that is between the positive and negative charges of atom, the dipole moment is increased from 0. So the distance of separation between the centers of the electron cloud and nucleus could be x. See in this previous diagram, now the separation distance is some more distance, let it be x. Since the nucleus is much heavier than the electron cloud, it is assumed that only the electron cloud is displaced when external field is applied. So it is just an assume because the nucleus is heavier. So it is not easy to move, it is not easy to displace from the equilibrium position. So now we are assuming that the nucleus is its equilibrium position, the only electron cloud is displaced when the external field is applied. Okay, so now the Lorentz force that equals to minus ZE. Now the Coulomb force equals to ZE into charge enclosed in the sphere of radius x by 4 pi epsilon naught into x square, the square of the distance between the dipoles. Now the charge enclosed is 4 by 3 pi r cube. R means distance. Here we are measuring the distance as x. So 4 by 3 pi x cube into density rho. That is, it is the negative charge density of an atom of radius r. Okay. So rho equals to minus ZE by 4 by 3 pi r cube. Let it be the volume. Now we are substituting the rho value in the charge enclosed, that is 4 by 3 pi x cube into minus ZE by 4 by 3 pi r cube. Finally we got minus ZE x cube by r cube. So that is the charge enclosed. Now the Coulomb force. See, what is the Coulomb force equation? ZE into charge enclosed in the sphere of the radius x. So the charge enclosed, that term will be added to this, and there is also 4 pi epsilon naught x square into r. Okay, so at equilibrium condition, the Lorentz force equals to the Coulomb force. We already said whenever those two conditions are equal. Okay, so what will happen? The Lorentz force equals to Coulomb force. So then our Lorentz force equation is minus ZE into E, and that equals to Coulomb force. Okay, let us see. So E equals to some value and X equals to some value. We know that displacement of two charges is proportional to applied field. So from this what we are knowing? Displacement of two charges is directly proportional to the applied field E. So induced dipole moment mu E equals to ZE x. Okay, so now the ZE into x term will be this. Okay, now finally mu E equals to 4 pi epsilon naught r cube into E. Okay, so we already know that mu E equals to alpha E into E. So where alpha E is the polarizability constant, so alpha E will be the 4 pi epsilon naught into r cube. So it is called a electronic polarizability constant. So here electronic polarizability is directly proportional to the cube of the radius of the atom, particular atom which we are considering. Okay, and next, the dipole moment per unit volume is called electronic polarization, and it is independent of temperature. We know this equation in the previous case, in the previous definitions. From that we are replacing these values. Now P equals to some value according to dipole moment equation, and P equals to, that is about permittivity. Now equating these two, we are getting the value of alpha E. Okay, here is some alpha E value and here is some alpha value. Okay, and next, ionic polarization. Now the ionic polarization is only for ionic dielectric materials. So the concept ionic polarization is applicable for the ionic dielectric materials. So let us see what are those. Ionic polarization occurs when atoms form molecules, and it is mainly due to a relative displacement of the atomic components of a molecule in the presence of an electric field. So whenever the ionic polarization occurs, when the atoms molecules, and it is mainly due to a relative displacements of atomic components of molecule in presence of field. So that is possible only when we are applying the external field, external electric field. So when electric field is applied to an ionic dielectric, then positive ions move in the field direction and negative ions move in the opposite directions. Hence dipoles will be formed. So whatever it may be, the charges are separating by applying the field. So positive charges will be move in the direction of the field and the negative ions move away from the, that means opposite direction of the field. Hence the dipoles will be formed. So this phenomena is called ionic polarization. Okay, ionic polarization. See, whenever there is no electric field, how the atoms will be, the dipole moments equal and cancel each other. Okay, and whenever we are applying the field, the positive ions move towards the direction of field and negative ions opposite to the direction of field. See, okay, now let us consider capital M and small m are masses of positive and negative ions respectively. So when electric field is applied on an ionic dielectric, then positive ions gets displaced in the field direction through x1 units of distance and negative ions displaced x2 units of distance in opposite directions. Okay, so the net distance between the two ions is x equals to x1 plus x2. Okay, now the Lorentz force acting on the positive ion is said to be E into E. The Lorentz force acting on the negative ion will be minus E into E. Capital E is known as a field. So when ions are displaced from their mean positions, then a restoring force appears on the ions, so which tend to move the ions back to their original position. So the name will be a restoring force or restoring force, whatever. Okay, now the restoring force acting on the positive ion is said to be minus K1 into X1, and restoring force acting on the negative ion will be K2 into X2 according to the force, or on the ions, positive ion and negative ion. So K1, K2 are known as a force constants, restoring force constants, and at equilibrium Lorentz force and restoring force are equal and opposite. Hence EE equals to K1 x1 and EE equals to K2 x2. So restoring force constants depends upon the mass of the ion and angular frequency omega naught of the molecules in which ions are present. That means x1 equals to EE by K1, that is equal to EE by K equals to M omega square, that is the M omega naught square. Like that x2 will be also. Now we know that x equals to the total distance, the total displacement x equals to x1 plus x2. Now x will becomes x1 term and x2 term, both we are adding. Now we are getting common from these equations. Okay, so induced ionic dipole moment mu I equals to E into x. So mu I equals to E square E by omega naught square into 1 by m plus 1 by small m. We know that induced dipole moment is proportional to the applied electric field. Okay, so mu I is proportional to E, and from the proportionality we are getting alpha I as proportionality, that is a polarizability constant. Here alpha I is the ionic polarizability. Now we are replacing the value. Okay, that is alpha I equals to, okay, alpha I equals to, from 7 and 8 we can write it as what's the value of mu I? Alpha I into E. E gets cancelled. And next, orientational or dipolar polarization. So orientation polarization occurs in polar substances. So these substances exhibit dipole moment even in the absence of external electric field. So for those past electronic polarization and ionic polarization, we are applying some external field. So without the field also, the dipole moment will be possible in orientational polarization, because those are the polar substances. These substances exhibit dipole moment in the absence of external field E also. Okay, next. Orientational polarization is due to the presence of polar molecules in the dielectric medium. So polar molecules have permanent dipole moments in the absence of electric field. So these molecular dipoles are randomly oriented, hence net dipole moment is 0. When electric field is applied, all the dipoles tends to rotate in the field direction. It results dipole moment, and this process is called orientational polarization. So even in the absence of the field, there is a dipole moment. Okay, so the orientation may be in random. So the molecular dipoles are randomly oriented, hence net dipole moment is 0. So to maintain the dipole moment, we are applying the field. Okay, so all the dipoles, what will happen? That will rotate in the field direction. It results the dipole moment, and this process is known as orientational polarization. But there's an example in methane molecule like CH4. The centers of the negative and positive charges coincide, so that there is no permanent dipole moment in the absence of electric field. So in certain molecules such as CH3Cl, the positive and negative charges do not coincide, because some charges are not coincide because due to their shape also. We said this, we know this in the early session of our class. So since the electronegativity of Cl is more than that of hydrogen, so electronegativity of Cl is more than that of the hydrogen atom. The Cl atoms pulls the bonding electrons to itself more strongly than hydrogen. So it will create a strong bond when compared to the hydrogen atom. So hence even in the absence of electric field, this molecules carries a dipole moment. So this is the reason behind some orientational polarization. So when electric field is applied on such molecules which possess permanent dipole moment, they tend to align themselves in the direction of applied field. So itself it will arrange the direction. It will arrange the direction of the atoms, direction of the charges due to the applied field. So the polarization due to such alignment is called orientational polarization, and it is depends upon temperature. With increase of temperature, thermal energy tends to randomize the alignment. So the alignment will be a randomized because the increase of the temperature. Okay, and next, orientational polarization P naught. So again here we are bringing the concept of polarization vector P. According to orientational polarization, P naught equals to n mu naught. Okay, 3 kt we know that it's a kind. P naught equals to all mu naught value replacing here. Okay, and next, from equations 1 and 2, alpha naught equals to mu square by 3 kt. So this is known as orientational polarizability. So the orientational polarizability is inversely proportional to the absolute temperature of the material. Here the temperature includes that we are maintaining that in the equation. Now according to our syllabus, we are considering these three polarizations, and out of the syllabus we are considering the space charge polarization. It is not a lengthy concept, you just go through this. Space charge polarization occurs due to the accumulation of charges at the electrodes. Now the ions diffuse over appreciable distances in response to the applied field, giving rise to redistribution of charges in a dielectric medium. So there is a concept of redistribution of charges due to the field. So such type of polarization is known as space charge polarization. So total polarizability is said to be, that is the sum of all individual polarizabilities like electronic polarizability, ionic polarizability, orientational polarizability, and finally space charge polarizability. Since the space charge polarizability is very small compared to all other types of polarizabilities, then so alpha S is negligible. So total polarizability equals to alpha E plus alpha I plus alpha naught. So due to electronic polarization and ionic polarization and orientational polarization. So we are adding by 3, we are getting the complete polarization. Hence total polarization is given by P equals to N into alpha total into E. So Ne into alpha total 4 pi epsilon naught r cube due to electronic polarization plus E square by omega naught square into 1 by m plus 1 by small m, that is due to ionic polarization, plus mu square by 3 kt, that is due to orientational polarization. So this equation is known as Langevin-Debye equation also. Okay, so this is the concept for types of polarization completely.